Hi all. In this presentation, we'll be working through a solution to the Connecting Territories programming challenge that appeared in the University of Waterloo's Junior 2025 Canadian Computing Competition. After we go through the problem description, we'll take a look at a dynamic programming approach that allows us to solve the problem efficiently while using very few resources. We'll take a detailed look at how the algorithm works and then walk through an implementation in Python and C++. So let's get started. Here is the problem description taken verbatim from the contest. Ava is playing a strategic game on a grid of tiles. Each tile has an associated cost. When the cost of the tiles are read from left to right, starting with the first row, a repeating pattern of the first m positive integers in increasing order is revealed. 1, 2, 3 up to m, followed by 1, 2, 3 up to m, and so on. In this pattern, m represents the maximum cost of a tile. In the grid of tiles shown, m is equal to 5. Ava needs to purchase one tile in each row in order to make a connecting path from the upper territory above the first row of tiles to the lower territory below the last row of tiles. The first tile purchased must be in the first row. Each subsequently purchased tile must share either an edge or a corner with the tile purchased previously. In the grid of tiles shown, the cost of Ava's connecting path is 9. Given a grid of tiles, your job is to determine the minimum cost of a connecting path between the upper and lower territories. And here is the input specification, also taken verbatim from the contest, along with an example input file and the illustration we saw before. The first line of input contains a positive integer r representing the number of rows in the grid. The second line contains a positive integer c representing the number of columns in the grid. The third line contains a positive integer m, where m is no greater than 100,000, representing the maximum cost of a tile. So in this example, there are 5 rows, 8 columns, and a repeating pattern of the first 5 positive integers in the cells of the grid. If you haven't tried this problem yet, why not pause the video now, try the problem, and then hit play again when you're ready to continue. There are actually 2 problems we need to solve. We could generate a 2D array to represent the grid of costs with values repeating from 1 to m, but that would use up a lot of memory, and some of the test inputs in the contest are huge. It would be much better if we could calculate the cost in a given row and column on the fly, because then there would be no need to go through the time and resource-heavy process of generating and storing all these costs. Fortunately, it is not too difficult to do just that. For example, let's say we are interested in the cost in the cell at row 4, column 5 in the example problem grid, highlighted in green here. How can we figure out that the cost associated with this cell is 4? One way is to consider the number of cells that appear before the cell of interest, highlighted in orange here. It helps to split these cells into 2 blocks, the cells that occur in the previous rows and the cells that occur in the same row but before the cell of interest. Let's consider the first block. If the cell of interest is at row R and column C, then the block of cells in the rows above the cell of interest has a height of r-1 and a width equal to the total number of columns. In other words, this block contains r-1 times columns cells. Now let's consider the block of cells in the same row but before the cell of interest. If the cell of interest is at row R and column C, then there are, of course, c-1 cells in this block. Thus, the total number of cells that occur before the cell of interest is r-1 times columns for the block of cells in the previous rows, plus c-1 for the block of cells in the same row but before the cell of interest. After that, we can group the total number of cells that occur before the cell of interest into ranges of cells containing the values from 1 to m. Here is the first range of cells with values from 1 to m. Here's the second range. the next range, the next, the last complete range, and finally, a few cells comprising an incomplete range that are remaining. Actually, we don't really care about the number of complete ranges of cells in this problem. We only care about the number of cells remaining, because that's what determines the value in the cell of interest. In this case, since there are only 3 cells remaining after we partition the cells into ranges, we know that the value in the cell at row R, column C, must be 4. Putting this together, if we have the row and column of the cell of interest, we first calculate the total number of cells before the cell of interest, and then take the remainder when we divide that total by m. Finally, since the cells start at 1 instead of 0, we just need to add 1 to the remainder to get the value in the cell of interest. So that's that problem solved. Now we need to think about how to find the least path cost as we traverse the grid from the top row to the bottom row. In this presentation, we're going to implement a dynamic programming solution. We first consider the case where there is only one row in the grid. In that case, the problem is simple. We just look for the least cost in the row to get the least cost of traversal. To solve the larger problem then, we consider how the cost will be updated as we add new rows to the grid. Let's see what that looks like. Here I have the first row in the grid, along with the cost of traversing the row at each column in an array shown in gray at the top. Remember that we don't actually need to store the values in the rows themselves because we have already solved the problem of getting these values on the fly. So we only need to create an array of costs. If this were the end of the problem, we would simply look for the least value in the costs array and we'd be done. Now, let's consider how the costs will change after we add the next row. For each cell in the new row, remember that we can enter from the diagonal left, directly above, or the diagonal right. Of course, for the first cell, we can only enter from above or the right, and for the last cell, we can only enter from the left or above. If we were to enter the first cell from above, the cost associated with this cell would be 1 plus 4 equals 5. If we were to enter from the right, the cost associated would be 2 plus 4 equals 6. The least of these two costs is thus 5, so we store this least value into a buffer array of costs, which we would need to create. Then we can move on to the second cell. If we were to enter from the left, the cost would be 6. If we were to enter from the top, the cost would be 7. If we were to enter from the right, the cost would be 8. Thus, the least cost, which we store to the buffer, is 6. And then we just continue similarly through the rest of the row. Once we have gone through the row, we update the costs by copying the values in the buffer array to the costs array. And then we're ready to move on to the next row. We repeat the steps for each cell as we did before, but this time we use the updated cost values as our starting points. For the first cell, if we were to enter from the top, the cost would be 7. If we were to enter from the right, the cost would be 8. Thus, the least cost, which we store to the buffer, is 7. And then we continue for the rest of the row as before. As before, once we have completed the row, we update the costs by copying the values in the buffer array to the costs array. And then we're ready for the next row. You get the idea. Let's continue until we have completed all the rows. At this point, we've worked through all the rows in the grid, and we're ready to find the least cost of traversal. We simply find the least value in the updated cost, which in this case turns out to be 9. And we're done. For this problem, we were only concerned with finding the least cost of traversal. If we were interested in the actual path associated with the least cost, we would have had to keep track of the decisions we made along the way. But again, that's not what we care about for this problem. Great. Now let's take a look at how this could be implemented in Python. First, we read in the number of rows, columns, and the period of the repeating pattern from the input file. Here is the function that calculates the value in a cell at row R and column C. Here we create the two arrays that we need, one to store the updated costs and one to store the intermediate buffer values. Here we set the problem up by starting with the costs of traversal for a single row. And here is the update algorithm. Starting from row 2, we go through each cell in the row. We calculate the cost for the cell. And here, I've arbitrarily first considered what the updated cost would be if we were to enter from above. If we can enter from the left, then we choose the least cost so far. If we can enter from the right, then we again choose the least cost so far. And finally, we save the least cost to the respective position in the buffer array. When we have gone through the cells in the row, we update the costs by copying the updated values from the buffer array to the costs array. When we have finished going through the rows, we simply search for the least value in the updated costs array. And finally, we output the solution. Exactly the same logic can be used for a C++ implementation. Let's include IOStream for input and output, and vector for our arrays. We define variables to hold the number of rows and columns and the period of the repeating pattern. Here is the function to calculate the value of the cost in a cell at row R and column C. And we're ready to begin. First, we read in the number of rows, columns, and the period of the repeating pattern from the input file. We create the two arrays that we need, one for the costs and one for the intermediate buffer values. Here we populate the costs array with the traversal costs that we would have if there were only one row. And here is the main update algorithm. For each row from row 2 onwards, and for each column in the row, we calculate the cost at that cell and arbitrarily start with the updated cost we would have if we were to enter from above. If we can enter from the left, then we take the least cost so far. If we can enter from the right, then we again take the least cost so far. And then we finally store the least cost into the respective position in the buffer array. When we are done with the row, we update the costs by copying the values in the buffer array to the costs array. And when we have gone through all the rows, we simply find the least value in the updated costs array. And then we output the solution, and we're done. And that's that. I hope you enjoyed the video. If you solved the problem using a completely different strategy, be sure to post in the messages below. Take care.